physics at the Benemérita Universidad Autónoma de Puebla. And something important to mention is that Antonio is one of the founders of the student chapter of artificial intelligence. So if in this room we have students, you can contact Antonio in order to join this student chapter of artificial intelligence. As a first approach to science research, Antonio had participated a couple of times in Haciendo Ciencia en la Benemérita Universidad Autónoma de Puebla. He has studied the variation of refractive indices of ethanol at different concentrations by surface plasmon resonance, and designing, building, and characterizing RCPC detectors for the ALICE LHC experiments. So we have an interesting combination of artificial intelligence with biology. So we expect that you can enjoy this tutorial. Before start, I would like to invite you if you have some doubts, please don't hesitate in raise your hand and ask Antonio any doubt or comment about the tutorial. So Antonio, if you are ready, the time is yours. You can start whenever you want.
Thanks a
So
lot,
thank
Roberto.
you again for your tutorial.
Thank you, Roberto. Well, my name is Antonio, and I am part of the chapter WAP of the SMIA, and I am going to give you a tutorial introduction to machine learning for material science. This with the environment orange, and I'm here in the name of the teacher Jesús Arzola. First of all, it's important to say that machine learning is playing an increasing role in our society, and more specifically in material science and engineering. This review seeks to provide a brief introduction to machine learning and its growing roles in an array of aspects of material science, as well as a more detailed discussion of the challenges and opportunities associated with using machine learning for predicting material properties and accelerating the design of these new materials. Well, as a brief introduction, machine learning can be defined as the use of computer systems that do not require explicit programming to learn about the tasks they are completing. Machine learning falls in two major categories: unsupervised and supervised learning. First one, unsupervised machine learning learns properties of data without any human guidance. For example, putting data into groups, that's also known as clustering, or finding dominant direction of data variation in high-dimensional spaces. This is the principal component in analysis. This unsupervised methods has the advantage of being able to analyze data with no need for humans to explicitly label that data, which is often a time and resource intensive endeavor. On the other hand, supervised machine learning would label data to learn a relationship between an output y and an input x, and is supervised in the sense that it must be told the value of y and the corresponding value of x. This type of learning includes traditional regression, for example, the multivariate linear regression, and more recent methods such as deep learning to find objects in an image. Supervised learning typically requires human input to label the data, for example, labeling objects in an image. Also, sometimes the computer can generate these labels by itself, for example, in a simulation. The potential of impact of machine learning, particularly in critical and economically massive areas such as high-tech businesses, manufacturing, national defense, and healthcare. This has led us to resources being committed to develop the machine learning ecosystem on the scale of billions of dollars per year in the United States and other countries. These resources have created an extraordinary opportunity for machine for our material science researchers to benefit from this ecosystem with only modest investment, somewhat analogous to the way computational material science has been enabled by an expensive commodity processor developed for other fields. Mm, okay, here we have the first graphic, and this shows us the growth of machine learning in material science and engineering, as seen in overall publications and review publications. We can see that the first 10 years of machine learning, the increase was very slow compared with the from 2014 for now. We have an increase very much faster. This examined a logarithmic plot for the data and suggests that since 2014 we have seen exponential growth, suggesting a doubling about every 1.6 years. In this review, we include both a high-level overview of areas and trends and a more detailed discussion of one specific central concern. Second of all is how is machine learning impacting material science, and is impacting in two different subjects. And the most important, the first one is the material property prediction. This is one of the most common and easy to understand uses of machine learning, and it consists in predicting new materials data from existing database. And we do this through regression y on x, followed by prediction of a new y and a new x. And that allows us to create new data in our database. This overall approach can be used to extend almost any database, as I said, in our new systems, allowing prediction of new data, rapid exploration, rapid exploration of larger spaces, and iterative optimization to find new materials. This is also called so, this is also called sometimes active learning. The use of machine learning in material science has been applied to predict myriad materials properties for many classes of materials, and this is a representative but not exhaustive list of recent studies, including to prediction of bulk stability of perovskite oxides. Here are the examples. The first one, as I said, is the bulk stability perovskite oxides. Also, another example is the uh, physiochemical properties of novel ternary compounds. The third one is the dielectric properties of perovskite and polymers. And the fourth one is the optical properties of metal and semiconductor nanomaterials. Then we have here a heat map. Is showing the detail. Well, sorry. Is detailing the number of newly discovered ternary oxide materials across the chemical space. This is prediction use were obtained by using machine learning to inform the probability of a ternary oxide will form. When too little data are available for regression, clustering can still provide a tool by grouping similar materials based on their features. To extend these groups, shared properties such as clustering can provide powerful predictions, and some used for finding these phase diagrams. Also, another application, here we have the detection of structural defects and mechanical properties in different materials using micrograph. This is a model labeled elliptical irradiation defects in a characterized steel micrograph. Then here we have a table that labels the material class with his application, the predicted properties, the initial training data set, and the machine learning algorithm. We can see materials such as inorganic ternary solids, molecules, polymers, metal alloys, perovskites, and metal organic framework, to name just one of them. Also, if you have if you want to check more this table, you can scan this code, and it will lead you to the article with this table. Next one, uh, the the steps we recommend you to apply in machine learning for material science. It can be described in five steps. First one is the data collection and cleaning. The second one is the feature generation and selection. It's also called featureization of future engineering. The third one is the model type selection, fitting, and hyperparameter optimization. The fourth one is the model uncertainty assessment, for example, the performance on test data, and also the domain applicability. The fifth one is the final model prediction. We can see this through this graphic. We load first the training data that goes to the descriptor representation. The training data could be the commercial database, some publication, the laboratory data, or a simulation made by the machine learning. Then we have the descriptor representation, and we set here what is our X income and what is our Y outcome. Here we have the chemical structure and also the domain knowledge. Then this description goes to the design space and the cross-validation. Here we are going to define where to search and to measure this performance. Then we set this data to the machine learning algorithm, and that is the model and data refinement. The machine learning algorithm drop results, and we need to interpret and visualize those results. Then the process. Then we need to validate this new data by experiments of theory. And if the data is correct, we set that data again in the training data. So we get new data in this process, and that is the cycle of machine learning. We also have to talk about the metrics to quantify this accuracy. Well, first of all, we have 4 different metrics to quantify this accuracy. The first one is the root mean square error. That is a commonly used error metric, and is frequently the error metric that the machine learning model seeks to minimize. That means that in the first metric. The second metric is mean absolute error. is also useful to calculate and will typically train with RMSE, but it is less sensitive to large error from outlier predictions and unlike root mean square error, is not smoothly differentiable, making it harder to use in some optimizations. Mean absolute percentage error is just the absolute error of as a percentage of the true data point value and is also very helpful as the importance of an error is often related to the size of the quantity being predicted. The third one is the coefficient of dependence R squared, which give us the fraction of variance in the true value that is predictable from the predicted values. This metric square R is always less or equal than 1, with 1 representing the perfect prediction and can be less than 0 for predictions that trend with the opposite side slope as the true value. The fourth one is given as r square red, and since it adjusts for the complexity in the model. It decreases when terms that have no predictable ability are added. Square error gives us a useful overall assessment of model quality, and generally values over 0.7 are desired for a useful model. Then here we have the how we are going to set our data to get better results in machine learning. We have three different categories. The first one is the training set. We the training set is the data to determine the optimal model parameters for a given model type, the hyperparameters, and the filter set. The second category is the validation set. They are instead used to assess the error in the model with optimal model parameters determined from fitting the training data. And then we have the last category, and is the test set, that completely left out and are not used in training or validation. Instead, they are used to assess the error in the final optimized model. Now we get the question, why using Orange? Um, First of all, Orange is an open source, so is accessible for everyone. The second is the Orange is machine learning and data visualization, allowed us to machine learning and data visualization. And the third reason is build a data analysis workflow visually with large and diverse toolbox. We have different toolbox such as time series analysis, image analytics, text mining, network analysis, and bioinformatics. Here we have the tools for data visualization. Um, some examples are the scatter plot, the heat map, the linear projections, and the box plot. Then the methods of learning model. As we said, they are two, and it's supervised and unsupervised. And some examples are the KNN, that is a regression and a classifier. Then we have the multi-layer perceptron neural network, that also is a regression and a classifier. The third one is the principal component analysis. For example, is TSNE. Then we have the tools for evaluating models. For naming son of one, we have the test and score. We have the confusion matrix. We have the ROC material analysis. Um, we have the calibration plot and the lift curve. And as I said, um, well, here for now on, we are going to do an example of the orange programming in machine learning. And the problem is here. We have this problem, and it consists of the typical classifier of iris flower dataset. So we have four different features um, and one target. The features are sepal length, sepal width, petal length, and petal width. This is our X income. And we have one target here that is our Y outcome, and is the iris specia. Here in this example, we have three different targets: the setosa, virginica, and versicolor. Here we have the data. The first column represents the sample, um, and the second, third, fourth, and fifth column are the features. That is, or attributes, or measurement, or dimensions. And the fifth one, the column five, is our target, and here is known as the class label. Also, we can see in the image the petals, what is the petal and what is the sepal. And the important of this is to know that the sepal length, the sepal width, the petal length, and the petal width are our four features that we are going to set in this process. And okay, the tutorial goes like that. First, of course, we need to start with Orange. So we open the software, and then we are going to click on the window of data. Then we are going to click on the widget of dataset. Well, the dataset widget serves to load a dataset from an online repository. The data, of course, is the output dataset, and this widget retrieves selected dataset from the server and send it to the output file, download it to the local memory, and is instantly available even without the internet connection. Each dataset is provided with a description and information on the data size, number of instances, number of variables, and the targets and tags. For this example, we are going to click, as I said, on the dataset widget, and we are going to select from the list the iris dataset. That allows us to load the dataset for this example. The second step, we now are going to select the data table widget. Is the one that goes here, and it allows to display attribute value data in a spreadsheet. We have the input, the data that we load before with the other widget, and the output will be the selected data and the instances selected from the table. Here we select the X point and the Y point. Well, the data table widget receives one or more datasets in its input and presented as a spreadsheet. The data instances might be sorted by attribute values. The widget also supports manual selection of data instances. Then we need to join both widgets by clicking on the bridge line of the datasets and dragging the link to the data table widget, as we can see here in the presentation. And it should be something like that. Then we are going to click on the data table widget, and now the data is uploaded. As we can see, Orange is going to open this table. Then we are going to visualize the data with a scatter diagram. This allowed us to get a better idea of the dataset. So we are going to click on the scatter plot widget. And we need to join, as we did it with the data table and the dataset. We need to join the dataset with the scatter plot, and we will give you click on the scatter plot widget. So we can see something like this. Okay. The scatter plot widget visual scatter plot visualization with explorative analysis and intelligent data visualization enhancement. We see the inputs are the data input set, the data subset, and the features list of attributes, as we said. Then the outputs are the selected data instances selected from the plot, and in data with an additional column showing where a point is selected. The scatter plot widget provides a two-dimensional scatter plot visualization for continued attributes. The data is displayed as a collection of points, each having the value of the x-axis attribute determining the position of the horizontal axis and the value of the y-axis attribute determination the position of the vertical axis. Various properties of the graph like color, size and shape of the points, axis, title, maximum point size, and jittering can be adjusted on the left side of the widget. Here you can see all that I'm talking about. In this case, we have three different categories: the setosa, versicolor, or virginica. So we can see separated of these classes of the targets, and we can see virginica as green, versicolor as red, and the setosa as blue. The next step in Orange is to select the Logistic Regression widget from Model Window. And this and also the evaluate window select and select the test underscore widget. We have here the test underscore widget and support various simple methods. First one is the cross validation, and this splits the data into a given number of folds, usually 5 to 10, and the algorithm is tested by holding out examples from one fold at a time. This model is induced from other folds, and examples for the held out fold are for the holdout fold are classified. This repeat for all the folds. The second sampling method is the cross-validation by feature. It performs cross-validation. Both folds are defined by the selected categorical feature from meta features. The third one is the random sampling. It just randomly splits the data into the training and testing set into given proportion. For example, 70 to 30. Then the whole procedure is repeated for a specific number of times. The fourth simple method is the leave one out. It's similar to the random sampling, but it holds out one instance at a time, introducing the model from all others and then classifying the held out instances. This method is obviously very stable, reliable, but is very slow. The next one is the test on trained data. It uses the whole data set for training and then for testing. This method practically always gives wrong results. And the last one is the test on a test data. The above methods use the data from data signer only, but this one use the input of another dataset with testing examples. For instance, from another file or some data selected in another widget, we select separate test data signal in the communication channel and select test on test data. And the other widget of logistic regression. Uh, the logistic regression classification algorithm with lasso L1 or rich L2 regularizations. The input are the in data is the input data, and also we can have the preprocessor uh, is a preprocessing method, of course, and the outputs are the interlearner is the logistic regression learning algorithm. In the model is the trained model. In the coefficients is the logistic regression coefficient. Well, the logistic regression learns a logistic regression model from the data. It only works with classification tasks. Number under which the learner appears in other widgets. The default name is logistic regression. Uh, the next step is to click on logistic regression widget and select the value of regularization. We, for this example, are going to wait. Click on test underscore widget and select the evaluation technique. And then we are joining the widget datasets and test score. Yeah, and in the other hand, we are joining the logistic regression with the test and score widget, as we can see here in the graphic. And then we are going to talk about the test and score widget in our metrics. There are two different categories, the classification metric and the regression metric. The first one, in classification, we have the area under ROC, and that is the area under the received operating curve. The second one, the classification accuracy, is the proportion of correctly classified examples. The third one, the F1, is a weighted harmonic mean of precision and recall. The next one, the precision, is the proportion of true positive among instances classified as positive. For example, the proportion of Iris virginica correctly identified as Iris virginica. The next one, to recall, is the proportion of true positive among all positive instances in the data. In this example, is the number of sick among all diagnostic ASIC. The last one is the specificity, and that is the proportion of true negative among all negative instances. For example, the number of non-sick among all diagnoses as non-sick. And in the other category of regression, we have the first one is the measures the average of the square errors or deviation, that is the MSE, and it represents the difference between the estimator and what is estimated. The next one, the RMSE, is, as we said, the square root of the arithmetical mean of the squares of a set of numbers, a measure of imperfection of the fit of the estimators to the data. The next one, the MAE, is used to measure how close forecasts or predictions are to the eventual outcomes. And the last one, the R2, is interpreted as the proportion of the variance in the dependent variable that is predictable from the independent variable. Then we are going to click on the test and score widget, and we are going to see the evaluation of these metrics. The next step is to click on the evaluate window and select the confusion matrix widget. Is the one that is here. And then we are joining the test and score and confusion matrix widget. Then we are going to click on confusion matrix widget, and we have this window right here. Now, but first we need to see what confusion matrix is. And the confusion matrix shows us the proportion between the predicted and actual class. The inputs in the evaluation results are the results of testing classification algorithm. The output is the selected data, is the data subset selected from confusion matrix. And in the section of data, the data with the additional information on whether a data instance was selected. The confusion matrix gives the number proportion of instances between the predicted and actual class. The selection of the elements in the matrix fits the corresponding instances in the output signal. This way, one can observe which specific instances were misclassified and how. Um, the next step in the window, you can see the confusion matrix of the logistic regression model, as we said. And here are our, our evaluations for the machine learning process. We have, for this example, 15 irisetosa and yeah, in the column we have the actual um, data set, and in the other we have the predicted data set. So are going here we are going to see where they are at, and that is all for the process of for this example. Um, well, another example is uh, here to solve a supervised regression problem in material science. Uh, the The metallic nanoparticles have interesting optical properties, such as their sulfur plasmon resonance, known as the SPR, which is an emerging property resulting from the interaction of electric fields with the conduction electrons of metals. Um, Here, the electrons absorb the energy of the electric fields, so a maximum is observed in their extinction spectrum. The SPR, that this is what we are searching. The extinction spectrum is equivalent to measuring the absorbance of a sample of the on the spectrometer. Um, so we said that we have light income to the nanoparticles, and the electrons of the nanoparticles are going to absorb the energy of this electric field. And we have here the graphic of of the extent of the wavelength of the wave, uh, again against the wavelength of our light income. And when the system is relaxed, it dissipates the absorbed energy in the form of heat, which can be used to eliminate cancer cells using a technique called hyperthermia. That is why this is very, very important. Um, Also, um, the position of the SPR as a function of the morphological characteristic of the nanoparticle is very, very important. So that is why the morphology can be manipulated with the nanoparticles synthesis technique. They knowing the SPR as a function of morphology give us an idea of which technique to use to tune the position of the SPR. So the problem is to predict the position of the SPR as a function of the morphology of concave gold nanocubes. And here the features are two. The first one is the edge leg, and the second one is the concavity. So we need to put the SPR in as a function of the morphology of this nanocube. And well, that in orange, we are going to load this dataset. Um, uh, First, we go to the data window and we click on SSV file import, so we can import the dataset into Orange. Then we are going to click on the widget and import the dataset that we want. Um, the next step is click on the select columns widget, as we did it with the iris problem. Then the widget appears and we click on select column widget and select the features and target. Here the length and concavity are going to be our features, and the target is the SPR. This widget, the manual selection of the allowed us to select the data attributes and the composition of the data domain. The inputs, of course, is the data. The outputs in data is the dataset with columns as set in the widget. So we set first the data, and it allowed us to select which one is going to be our target and which one is going to be our features. The next one, we are going to click on visualize window and select the scatter plot widget. And then as we did it with the iris problem, we are going to join the select columns and the scatter plot widget. So the data is now loaded into the scatter plot. Then, yes, that's all. We are going to click on the widget. We are going to select the length and the SPR. So we get in the graphic, in the x-axis, the length, and in the y-axis, the SPR. Also, we can select the concavity as a color difference. So the first one, the blue one, is the ones with concavity 1 to 1.25. The green ones are the one with concavity 2, and the third one is with concavity 3. We can see the separate the different classes of gold nanocubes. Then we are going to click on the model window and select linear regression and neural network widget. And also we are going to select the test and score widget from evaluate window. First one, the linear regression widget, is a linear regression algorithm with optional L1, L2, or L1, L2 elastic net regularization. Uh, the linear regression widget constructs a learner predictor that learns a linear function from its input data. This model can identify the relationship between a predictor X and the response variable Y. Additionally, lasso and ridge regularization parameters can be specified. Lasso regressions minimize a penalized version of the least square loss function with L1 norm penalty and ridge regularization with L2 norm penalty. The inputs in the data is the input dataset. The preprocessors are the preprocessing methods. The outputs are the learner. In the learner is the linear regression learning algorithm. In the model is the trained model. And in the coefficients is the linear regression coefficient. Then in the other widget, the neural network widget use Sclear's multi-layer perceptron algorithm that can learn nonlinear models as well as linear. So this is a widget more completed than the linear regression. Now this is a multi-layer perceptron algorithm with backpropagation. And in the inputs, the data, of course, is the input dataset, the preprocessors, um, as as in the linear regression is the preprocessing methods, and in the outputs, in the learner is the multi-layer perceptron learning algorithm, and in the model is the trained model. Um, Also, we have to talk about the model parameters of this set. Uh, First, we have the neurons per hidden layer. Is defined as the ith element represents the number of neurons in the ith hidden layer. For example, a neural network with 3 layers can be defined as 2, 3, 2. Then the set model of activation function for the hidden layer. Here we have 4 different ones. The identity is a non-operative activation, and it is useful to implement linear bottleneck. The second one, the logistic, is the logistic signal function. The sun, the hypertank is a hyperbolic tank function. Uh, ReLU is the rectified linear unit function. That all for the activation function of the hidden layer. Then in the solver for weight optimization, we have these 3 different ways of optimize the dataset. The first one is an optimizer in the family of quasi-Newton methods. The SGD is the stochastic gradient descent, and Adam is the stochastic gradient-based optimizer. Then we have the alpha set model is the L2 penalty L2 penalty parameter. And the last one is the max iterations, is the maximum number of iterations. And also we can set other parameters to exclude the file. Next, in orange, we are going to click on linear regression widget and select L2 regularization equal to 1, as we can see here in the screen. The next step is click on neural network widget and select alpha equal to 1, 10 neurons in one hidden layer, activation function as ReLU, and LBFGS solver, as we see here in the caption. The next step is click on the score widget and select 5 full cross validation. For the last one, we are going to join the select columns and the test underscore widget, and also the linear regression and the test underscore widget, and finally also the neural networks and test underscore widget. And we here have the how it is going to be. And we click on the test underscore widget, and you can see here the evaluation metrics and model comparison. The number in the table gives the probability that the model corresponding to the row is better than the model corresponding to the column. If negligible difference is enabled, the smaller number below shows the probability that the difference between the pair is negligible. The test of comparison is based on the Bayesian interpretation of the t-test. And that is all for the nanoparticles problem. Also, right now, there is a wide variety of databases, such as these 3 examples. First one, the material project. Second, the superconductive material database. And the third one, the open quantum material database. So it is possible to implement machine learning to accelerate the discovery of new materials. And also, here are other tutorials to know more about the Orange program. And you can scan it here in this code. And that is all for the presentation. Thank you very much.
Thank you, Antonio. Thank you very much for sharing with us this interesting software, Orange. Most important, how do you apply to this kind of applications? We really appreciate the information that you share with us. And if anybody of the audience has any question, please raise your hand, or if you prefer, you can directly contact by email to Antonio for any question that you have. So let me see if somebody has a question. Nobody raises his hands, so let me finish then this session. And before to finish, I would like to read the diploma that we are going to send you for this interesting topic. So right now I'm sharing you the diploma, and I would like to read. The Mexican Society of Artificial Intelligence and the Universidad Panamericana awards this certificate to Antonio Zuñiga for giving the tutorial Introduction to Machine Learning for Material Science with Orange. at the 19th Mexican International Conference on Artificial Intelligence. This diploma is signed by Dr. Felix Castro, who is the SMIA president, Dr. Lourdes Martinez, who is the program chair, and Dr. Oscar Herrera, also program chair of the MICAI, and Dr. Iran Ponce, who is the local chair of this edition of MICAI, Mexican International Conference on Artificial Intelligence. So thank you so much to everybody, especially to you, Antonio. We invite to all of you to continue participating in the different activities of MICAI. Remember that everything is online virtually, so we have also already the workshops, and tomorrow we are going to start with the keynote speakers and the presentation of the different papers that sent to the conference. I am reading some questions in the chat. Let me see. There is a question from Marcela Marquez. Marcela Marquez says that the QR code that you share has a restricted access. So if you can help us to solve this and they can access by using this QR.
In which one specifically? In which
Marcela,
one?
just one of them, but if you can tell us which one.
Please.
Was one of the first?
At the beginning of the presentation, I think.
Okay. I'm going to share the presentation again.
Okay, go ahead.
One of the first ones you said, right?
Yes. Maybe the second slide.
No.
You told me.
No. Next. Was that one that says now we will solve a supervised regression problem?
Okay. Wait.
Tools. Maybe that one. One slide before.
Okay.
Maybe that.
No, it has the metallic drawing, the gold one with length and deep radius.
The gold one? Yeah, the nanoparticle, right?
Right.
This one.
Yes.
It don't scan? Wait a second. I will scan it with my cell phone. Oh yes, it has an error. I can share you the database if you are interested in this article. I could load it to the. No,
Sorry, Antonio. Maybe it could be easier if you can correct the QR, and if you send me the presentation, we can upload in the website of MICAI in order to everybody can download again.
Yes, please. That would be very good.
Perfect. Thank you, Marcela. Please keep in contact and visit the web page in order to download the updated presentation with the corrected QR.
QR, cool.
Okay, thank you very much. So another question.
Thank you a lot, Roberto.
Nobody? Okay. So if nobody has questions, it's time to finish this session. once again, thank you, Antonio, for your tutorial, and thank to everybody for attending this tutorial. And see you in the different activities of MICAI 2020.
Thank you, Roberto, and thanks all for your time and to see this presentation. Thank you a lot.
Thank you. Goodbye.
Goodbye.